We have 5 common types of model equations that involve exponential and logarithmic functions. 2 of them we're quite familiar with, exponential growth and exponential decay. In both of these examples we see that E is the base in our model, but it could be some other base. But typically for model equations we'll go with E as that base and then just use some coefficient B in front of the x to help adjust it. We also have this Gaussian model. We are not going to spend any time on this one, but this is a model that creates a bell-shaped curve. So a lot of times you'll hear about like a bell curve that's used for curving grades or that sort of thing. So that's generally based off of a Gaussian model. Then we've got logistic growth, which is an interesting type of function, which is for circumstances of constrained growth, where you start off with exponential growth. That's what we see in the early part of the curve, but then there's some sort of limiting factor, so then that growth starts to taper off and approaches some sort of maximum value. So we'll see an example of that before too long. And then the last two here come together are logarithmic functions. So again, we're just demonstrating this with 2 different bases, but those are both logarithmic functions. And so just depending on whether the base is E or the base is 10, you're going to get a slightly different shape. We also, in these 2 particular examples, have a 1 that's out front, but that's not a necessity. But that makes it so that the graph will go through, instead of 0, 1 or 1, 0, it'll go through 1, 1 in all cases. So these are the 5 different types of functions. Exponential growth and decay are 1 and 2, the Gaussian, which we're not going to use, logistic, and then we've got our natural logarithmic and common logarithmic, which basically count as 1. So one example of a exponential decay model is used for trying to carbon date items. So in a material, the carbon isotopes, there are 2 primary carbon isotopes. There's the stable carbon-12, and then there's a radioactive carbon-14. And so those are continuously replenished in your body in an organic material as it lives. But once it dies, the carbon-12 stays static, whereas the carbon-14 begins to decay. And so then depending on how much carbon-14 compared to the carbon-12 is left, as it decays, there's less of it while the carbon-12 stays stable. So as we see how that ratio changes, we can use that to determine the approximate age of some sort of organic material, how long ago it had died, how long ago it stopped replenishing that supply of that radioactive carbon-14. And so the equation for that is shown here. And so we can see that this is an exponential decay model. We do have some coefficient here, 1 over 10 to the 12th. We've got our natural base E, and then we have a negative in front of the variable along with this B value of 1 over 8223, which is unique for this particular type of carbon. In the case of some other radioactive material that decays faster or slower, everything will be different in terms of the coefficient that's out front here, as well as this number. But for our purposes, for this decay of this carbon-14, this is the model equation that we can use. And so what we're told is that the ratio of this carbon-14 to carbon-12, which is what the R variable represents in our equation, for some material that gets found, some fossil, is 1 over 10 to the 13th. So that's the value that we're going to plug in for R, and then we want to figure out how old it is by solving for T. So if we do that, I plug in 1 over 10 to the 13th equals 1 over 10 to the 12th, e to the negative t over 8223. So there's our equation with that value plugged in, that ratio plugged in. So I can see that my variable is inside of my exponent. So in order to solve, I'm going to need to get that variable out of the exponent, which means I'm going to have to use logs. But before I can use logs, I need to isolate the exponential. So I'm going to multiply both sides by 10 to the 12th. And so if we do that, we're going to get 10 to the 12th over 10 to the 13th. So that's just going to reduce to 1/10. And then on the other side, we still have e to the negative t over 8223. And so now that we have the exponential isolated, we can rewrite this as a logarithm. That's the only way that we're going to get that t out from the exponent. So the base of my exponential is e, so the base of my log is going to be e. So it's going to be the natural log of the output of the exponential, 1/10, is going to be equal to the exponent, negative t over 8223. And so now at this point, we're just in button pushing territory on our calculator. We need to find what the natural log of 1/10 is. So if I move over here and I do that on my calculator, I get negative 2.303. So that's equal to negative t over 8223. And so then my last step is to just multiply both sides by that 8223, but I'm actually going to multiply both sides by negative 8223, so my t ends up positive. And so if we do that, we round off to the nearest year. Not that we would really know to that degree of accuracy, but we can go ahead and do that here. We get 18,934 years since this fossil had been alive.